I'm Lucy. I'm a fourth year grad student in Jeremy Manning's lab at Dartmouth, and today I'm going to be talking about how we're trying to understand interactivity of brain patterns through higher order correlations. And particularly, I'm going to be talking about a method that we've developed called timecorr that allows us to estimate higher order correlations in a computationally tractable way. With this project, we wanted to understand what neural activity patterns change over time and support cognition. And possible neural patterns could be univariate, which characterize the activity of individual units. And they could be Jim-Haxby-style multivariate patterns, which characterize the patterns of activities across units. And these patterns could either be static or dynamic, and they could be within and across brains. But there's also the order of the interactions of those patterns to consider. And so these could be raw activity patterns, which we refer to as order 0. However, they could be network patterns, which we're referring to as order 1, and these could be seed-based connectivity or following work from your group and others, functional connectivity. And then the patterns of those patterns would be order 2 patterns. And this is the same idea that your group has been discussing with edge functional connectivity. But what about orders beyond the second order patterns? What about 3 and above? So this might look pretty familiar to your groups working on edge functional connectivity. But to give you a more concrete example of higher order correlations, here's a diagram of 4 brain regions, A, B, C, and D. First, the raw activity patterns or order 0 correlations are shown. Next, the dynamic first order correlations show how A and B as well as C and D are related over time. And finally, the dynamic second order correlations reflect the correlations between those pairs of first order correlations. And then to the right, I'm showing all the other possible first-order combinations. So if the dynamic correlations between those 2 regions, A and B, is similar to the dynamic correlations between the 2 other regions, C and D, then this would be reflected in the second-order correlations between those pairs. So second-order correlations reflect homologous patterns of first-order correlations. And again, up to the second order, our approaches are very similar. But the framework I'm going to be talking about next is a framework that you can extend to even higher order correlations, so order 3 and beyond. So for example, the third order correlations would reflect homologies between second order correlations and so on and so forth. So with this project, we wanted to explore whether higher order dynamic interactions between brain structures support our thoughts, particularly because higher order dynamic interactions may be better at characterizing the complexity of the brain, a system that operates on multiple scales of time and space, and that can be decomposed into subcomponents at many scales and the interactions between those subcomponents. And so we wondered if dynamic higher order correlations could decode mental states, and if so, at what order of interactions. But first, how do we actually compute these higher order correlations? So we first use a kernel-based method following approaches of statistical physics in the 60s to compute dynamic correlations. And we take a time points by features data matrix and compute a time-varying correlations, which outputs a time points by features squared matrix. And we do this by incorporating a weight function. So here I'm illustrating this with a Gaussian weight, but one of the parameters that you can change is the kernel shape. So to calculate higher order correlations naively, we would square the number of features of each order, and the computations would grow exponentially. And this becomes computationally intractable even with just a few features very quickly. So to make the computations tractable, once we have the dynamic correlations, we then project those correlations into a lower dimensional space, the original size of the time points by features data matrix. And there are several ways that we can project these correlations into that lower dimensional space. We can use dimensionality reduction algorithms, also known as the kernel trick, and the resulting dimensions would reflect weighted combinations or nonlinear transformations of the dimensions of the original space. But we can also use graph measures, which characterize each unit's participation in its associated network. So for example, we can look at how the node positions change over time, and that can be similar for 2 different nodes, even though their underlying activity patterns would be totally different. And so also one perk of graph measures is that you can easily map that back onto the original feature space. So even calculating something like the 30th order correlations, those could be mapped just as easily back onto the original feature space as second order correlations. And so in a way, these provide parallel directions. So using dimensionality reduction, retains the specific activity but with a lower fidelity, while using graph measures kind of throws away the information about the specific activity but retains the interactions. But using this trick of projecting into lower dimensional space allows us to repeat this process over and over again and estimate at any arbitrary higher order correlation. And this computation, instead of increasing with the square of the features, now just increases linearly. So for example, we examined 15th order correlations in the neuroimaging data set that I'm going to be talking about in just a second. And using conventional methods, that would have required storing roughly 32 times as many bits as there are molecules in the known universe. So we actually include these 15th order correlations in our paper just to demonstrate the feasibility of this method. So using this method we developed, we wanted to explore how higher order interactions change with respect to higher order cognition, while preserving low-level properties using a naturalistic storytelling dataset. And this dataset that we're using was collected by Uri Hassan's group, and participants were scanned while being told a story from the Moth Radio Hour called Pie Man. And the story was told either intact, or it was paragraph scrambled, or word scrambled, or they were scanned just during rest. So to give you a sense of what these experimental conditions are like, here's 4 sentences from a completely different passage that I've word scrambled. And I'll give you a second just to look this over. So some of these words might give you a clue as to what's going on. Maybe it's directions for something, maybe it's something food related, maybe it has to do with a pie. So even though each of these words individually are meaningful, there's a lack of a depth of processing that when you decontextualize them. Now, I won't show you a paragraph scrambled version, but just to give you an idea, here I've scrambled the sentences. And I'll just give you a second to read this over. So with the paragraph scrambling, you might get a bit more of a narrative structure, but even adding the structure of the sentence, you start to understand the passage more and more. And so connecting words temporally by adding the structure of the sentence, you gain a depth of processing. And finally, with the intact structure, it's just a fluid read and you can completely understand the narrative. It's just directions on how to make a pie. And so natural processing not only connects words temporally in the structure of the sentence, but the sentences are also connected meaningfully. So we used a subset of the data to train across participants classifiers to decode listening times. And we trained the classifiers using iteratively increasing orders of dynamic correlations, which we inferred using our method. And by training decoding models on different types of neural features, we can better understand which specific aspects of the neural activity patterns are informative and important for higher order cognition. And what we're decoding here is based on just neural data. Can we predict when in the story someone's listening? Specifically, we're using an across-subject decoding, which means that the decoding accuracy relies on patterns of being similar across subjects. So across all conditions, subjects' brains are exhibiting very complicated brain patterns, but in this analysis, we're just assessing the stimulus-driven thought. And the way we're assessing this is using a really strict criterion for accuracy. So if it's not the exact time, then we're going to treat it as incorrect. So we treat 2 seconds off as being the same as 2 minutes off. And it's not because we don't think that closer time points aren't related. We just want a really sensitive measure. So I'm going to show you decoding accuracy as a function of the number of orders of correlation in that decoder. And it could be that the best decoding accuracy comes from just the raw data, which would be the order 0 patterns. And in that case, adding more and more higher order interactions would be uninformative and noisy and would just decrease the decoding accuracy. But it could also be that as we add more and more levels of interaction, we could decode better than just the raw data. So just to quickly orient you with the results, the line colors are associated with the condition, and the arrows show the decoding accuracy where it's reliably above or below the mean decoding accuracy. And the y-axis is relative to chance, so 0 here is chance decoding. And the circles denote the order where the best decoding accuracy was achieved. And looking at these results, you can see 2 things. One is that the story is as the story is more temporally structured, the better the decoding accuracy. So the intact condition overall has the best decoding accuracy, then the paragraph condition, then the word condition, then the rest. And second is that the story is more structured, the higher order patterns become more informative. So for the intact condition, the classifier that performed the best included a blend of dynamic higher order correlation patterns up to order 2. While the classifier trained on the scrambled story or the resting state data, only lower order dynamic patterns were informative to those decoders. Also, the correlations used to obtain these results were calculated using PCA as the dimensionality reduction technique. And so the next thing I'm going to be showing you is that the same results on the left, however, we perform this analysis using eigenvector centrality to calculate the correlations, and those are shown on the right. And although the PCA reduced values are a fuzzy reflection of the activity, and the eigenvector centrality reduced values show the participation of the nodes, and even though they're capturing different information, with these two measures of decoding results, they're actually qualitatively very similar. So we found the best decoding accuracy for the intact story listening condition for both, and the classifiers that we used that performed the best included a blend of dynamic higher order correlation patterns. And so taken together, our results suggest that higher level cognition is supported by higher order dynamic patterns, and that possibly up to fourth order correlations can be informative. But another interpretation is that with fMRI, we can only reliably record up to that level of interaction. And so we need more, we need to explore this more with different types of data. We next took the average dynamic correlations at each order, and we looked at which regions mediated the interaction patterns at different orders by finding which brain regions most reliably reflected the different orders across people. And we then ran a meta-analysis using Neurosynth to find the top 5 terms for each of those regions. And so for all of the story listening conditions, the intact, paragraph, and word, we found that the lowest order patterns were mediated by lower level auditory patterns. Specifically, that first and second order correlations were most strongly associated with auditory and speech processing areas. But with the temporally scrambled versions of the story, the terms associated with higher order correlations involved, again, mainly additional regions associated with speech and semantic processing. However, during intact story listening, the third order correlations reflected integration with visual areas, and then fourth order correlations reflected integration with areas associated with high-level cognition and cognitive control. And in contrast, this is a really different set of patterns in the resting state data, where the story listening conditions involved regions involved in processing the story. We didn't see that in rest. Instead, there are more regions reflected in episodic recall and spontaneous memory. So our findings suggest that higher orders of network interactions support higher level aspects of cognitive processing. And when tasks evoke richer, deeper, and higher level processing, this is reflected in higher order network interactions. Okay, so to wrap up, we created a computationally tractable framework for approximating dynamic higher order correlations. Using our method, we found that higher order interactions were reliably conserved across participants. And when tasks evoke richer and deeper higher level processing, this is reflected in the higher order network interactions. And we also found that higher orders of network interactions support higher level aspects of cognitive processing. I'd like to thank my lab and my advisor, Jeremy, and also our collaborator, Tom Chang, who's now working at Amazon. And if you have any questions, please feel free to reach out to us. You can also check out our lab website, contextlab.com, for more information. Thanks.